So we're going to go ahead and look at the structures and behavior of specific acid and base groups, and basically come up with a few means to identify if something is going to behave as an acid or a base. Okay, so based on what we've been discussing so far, the question of what makes something an acid. The Bronsted-Lowry definition, states that an acid puts protons into solution. Okay, so basically any molecule that has a hydrogen that potentially could be ionized into H+, is going to potentially be an acid. However, just because it potentially could be ionized doesn't mean that it actually will be. So not everything that could be an acid is an acid. Okay, so a few examples of substances that have a hydrogen atom in the molecule that are not actually acids would be chloroform that we see here, okay, nitromethane, okay, here. And the reason why these hydrogens do not get ionized into H+ ions is because carbon-hydrogen bonds are very, very strong and non-polar. There's basically no difference in electronegativity between carbon and hydrogen. So these molecules do not have a tendency to donate their hydrogens to the solution. Okay, so there's going to be three factors that we're going to look at to determine if a molecule with a hydrogen atom in the molecular structure will behave as a Bronsted-Lowry acid. Okay, and those features or those things that we're going to be looking at are polarity, bond strength, and of course the stability of a conjugate base. Okay, so the first feature that we're going to look at is bond polarity. So what we mean by bond polarity is the way in which electrons in the bonds are being shared. Okay, so if we look at hydrogen and fluorine in this HF molecule, we know that fluorine is way more electronegative than hydrogen, and so what ends up happening is the electrons that are being shared in this bond right here are being shared unevenly. So that gives us a polar covalent bond. And what that means is that there's going to be more electron density around the fluorine atom than around the hydrogen atom. So we know that HF is a weak acid. So one might ask, well, if HF is a weak acid, but, there's a huge difference in electronegativity here, why is HF not a stronger acid? And that's because we have to consider another feature of what's physically going on here. So HF, even though there's a large degree of polarity between the hydrogen and fluorine atoms in the molecule, there's also a relatively high bond strength. So there's really good orbital overlap, and so that bond strength is really high. Okay, and so that brings us to our second point, or our second factor that we need to consider, which is bond strength. And basically, bond strength is the energy that's needed to break a bond between elements in a compound. And we've already discussed bond strength earlier in the semester. So basically, this is actually going to be a really big factor in determining hydrohalic acid strength, and it's going to actually affect the relative acidity of a specific acid much more than bond polarity. And we'll look at this here in a little bit. Okay, so right here we have a nice listing of the hydrohalic acids you guys should be familiar with, right? Hydrofluoric, hydrochloric, hydrobromic, and hydroiodic acid. Okay, and we know that as we go from left to right in these examples, we know that the electronegativity differences between the hydrogen and the fluorine is becoming smaller and smaller. So basically we know that each one of these molecules is going to be slightly less polarized. With HF, of course, being the most polar, because fluorine is the most electronegative element, and HI being the least in this group, because obviously iodine is way far down on the periodic table, and subsequently doesn't have as high an electronegativity value as fluorine. Okay, so if we notice this trend, basically we're going from most polar to least polar. And if we look at this trend, while we also look at relative bond strength, okay, I want you to notice that the bond energy, the energy required to break the HF bond, is much larger than the bond energy of HI. Okay, and so what you notice here is that bond strength and bond polarity are not necessarily going to be in the same vein or in the same trend. So what you need to consider is that in the case of hydrohalic acids, the reality of it is that the bond strength is going to be the determining factor for the overall strength of the acid, or the overall donation capabilities of the protons in each one of these acid molecules, acidic molecules. Okay, so what we see here is we see that HF is a weak acid, right? That bond strength is very high, so it's going to be very hard to ionize that H+. Okay, HCl, HBr, HI, okay, these are all examples of strong acids, and basically what you notice is that you see a pretty significant decrease in the overall bond strength for each of these molecules. So remember, when we're dealing with hydrohalic acids, or these hydrogen halides, as some texts like to call them, you're going to have to consider the bond strength over the bond polarity. So let's go ahead and move on to some other charts that will allow us to kind of solidify this idea. Okay, so for hydrohalic acids, okay, the stronger the bond, the weaker your acid is going to be. Okay, so basically we know our electronegativity is decreasing down the table, so we know the polarity of our molecules here is decreasing. However, if we take a look at bond enthalpy, okay, that the energy required to break that bond, we know that the bond energy of HF is going to be way, way higher than, say, HI. So in this case, when we look at the ionization process of HI, okay, we know that it's going to be much easier for HI to put this H+ into solution because this bond is easier to break. All right, so make sure that you guys are connecting all these trends, that you're spending a little bit of time to think it through. It can get a little bit fuzzy, but as long as you straighten everything out in your head, you should be able to always tell me why, HI would be a stronger acid than HF. Okay, so the third feature we have to look at when considering the strength of an acid, okay, is the way in which the charge on the conjugate base is stabilized on the molecule. So basically we know that whenever we ionize an acid, okay, we have HA going to H+ and some conjugate base. Okay, so this charge that's on this conjugate base is going to be stabilized across the molecule or across the atom. Now, depending on the features of the molecule in which that charge is being distributed, that's going to dictate the overall stability of your conjugate base. So things like resonance, okay, and the size of the ion are going to be dictating factors related to the acid strength. So what do I mean by resonance? Well, if we look at, say, like HNO3, right, it's going to produce H+ and NO3 minus. Okay, well, if we look at the Lewis structure for this conjugate base, we know that we end up with basically this Lewis structure, and we know that the charge that exists on this ion is basically going to be distributed amongst the various oxygen atoms in the molecule, because we could draw a resonance, as we've discussed, okay, in a couple of other forms, right? Okay, and of course, the third option okay, and basically this resonance structure allows us to see that this minus charge is actually distributed all across this molecule and spread through the various oxygen atoms in this molecule. So that helps stabilize that charge because it's not just centralized on one of the single oxygens within the molecule. So in the same thought process, usually the larger your anion, the easier it is for that charge to be distributed and not as centralized and concentrated. So basically the resonance features that we talked about here, or basically having a bigger conjugate base anion, so a larger atom, that the charge can basically rest on is what's going to facilitate additional stability. So when we're looking at oxyacids, okay, or acids in which you have a hydrogen attached to one of the oxygens in the molecule, we can look at a series of related oxyacids and relate their strength to the number of oxygen atoms present. So basically, you know, HClO4 has 4 oxygens, HClO3 has 3, 2, 1, etc., right? Okay, so basically, the more oxygen atoms you have, the more likely your acid is going to put H plus into the solution. So basically, the more oxygens you have, the more acidic your acid will be. And why is this? That's because oxygen atoms are very electronegative, and so what happens is that the more oxygens you have in the molecule, the more they're able to draw electrons away from the other elements, hydrogen being one of them. Okay, and so this is going to polarize and weaken the OH bond and subsequently make it where the hydrogen is easily ionized and subsequently allows this oxyacid to behave as an acid. So we can look at a quick diagram to help us visualize this. Okay, so these are all the oxyacids that we were discussing before. Okay, notice our HClO4, our HClO3, our HClO2, HClO. Okay, and in each one of these examples, okay, notice that there's a hydrogen attached to one of the oxygens. Okay, and so what ends up happening is that the electron density that's being shared between the oxygen and the hydrogen is, obviously being pulled towards this oxygen. However, when you have additional oxygen atoms attached, okay, they too are pulling electron density away from this bonding set. Okay, so the electron density is being pulled towards these other oxygens, and subsequently you have less electron density on this hydrogen than in the example here. Why? Because in the example here, we only have 3 oxygens pulling away from the hydrogen as opposed to 4. Okay, and that same trend continues when we look at, obviously, HClO2 and HClO. So basically, your H plus is going to be more easily ionized the more oxygens you have in these oxyacids. And remember, we're comparing these in a group that are all related. Obviously, everything's basically the same structurally except for the number of oxygens. Okay, so we're going to look at oxyacids a little bit more. Okay, we have to consider also the Z group that's involved in the oxyacid. So in the previous examples, chlorine was the example that we looked at. Okay, but obviously the Z could be any other element. So how are we going to treat oxyacids with respect to Z? So we know that the OH bond is going to be easier to break if basically more electron density is being pulled away from the OH bond itself. Okay, so the more we polarize this, the easier this process is. Okay, so if Z is very electronegative, you're going to end up with obviously more electron density being pulled towards the Z. Okay, and subsequently this is going to polarize this bond even more and subsequently make this hydrogen easier to ionize and make this overall ionization process easier. So it's going to make the oxyacid even stronger if Z is more electronegative. The same thought process applies if you have a high oxidation state with respect to Z. Okay, so the higher its oxidation state, the more we're going to polarize this bond here because we're pulling electron density away from it, and you subsequently get a stronger acid in that respect. So let's go ahead and look at a few examples. Okay, so oxyacids that have different Z central atoms that are from the same group and have the same oxidation number are going to be directly related to the electronegativity value. So the acid strength is going to be dictated by electronegativity. Why? Because these all have the same oxidation number, they're all in the same group, so the comparison can be made directly. So the more electronegative you are, okay, the higher the electronegativity, basically the more polarizable, or the more polarizable the OH bond is going to be, right? So I'm pulling electron density towards bromine, I'm pulling electron density towards chlorine, but since chlorine is the more electronegative of the two, this bond right here is going to be more polarized than this bond here. Okay, so what ends up happening is HClO3 is going to be obviously more easily polarized or more have an easier time putting H plus into solution than HBrO3. Okay, and notice, guys, we're comparing things with the same number of oxygens, right? Basically almost the exact same structure. The only difference here is that we're dealing with different Z elements. Okay, so if we go ahead and look at oxyacids that have the same central atom, so that same Z, okay, but have a different number of attached groups, we are going to be able to decide the acid strength based on the oxidation number of the Z group, right? So if we look at the hypochlorous acid, okay, our oxidation number of this chlorine, or the Z element, is going to be +1. Okay, this one will be +3, this one will be +5, this one will be +7. Okay, so the higher the oxidation number of Z, that's going to create a more polarizable situation for the OH bonds in each of these. So as we have higher oxidation states or oxidation numbers for that Z element, we're going to have more acidity. So HClO4 is a stronger acid than HClO3, and HCl2, etc. So hydrated metal ions, we've already discussed these before, but let's take a look at what's actually happening here now that we're discussing this acidity property series. So basically, we've talked about the fact that highly charged metal ions, like aluminum +3 or Fe +3, can basically create an acidic solution. And what that is caused by is the fact that the charged metal ion, when it basically chelates these H2O molecules, pulls the electron density away from the OH bond. Okay, and basically it polarizes this OH bond and makes it subsequently easier for, another water molecule to come around, okay, and subsequently ionize off, okay, this hydrogen. And so basically we're able to put H3O plus in solution and subsequently create a acidic situation. Okay, so similar vein to what we were just talking about, the greater the charge, the more acidic a situation you're going to have, just like the oxidation numbers in the other examples that we were looking at. Okay, so let's go ahead and look at the acid-base properties of oxides. So another way that we can look at identifying whether something will behave as an acid or base is to look at how the hydrogen that's attached to an oxygen is connected to the remainder of the molecule. So if this HO is attached to the other component of the molecule in a covalent way, you're going to end up with acidic solutions. Okay? If the OH is attached to the remainder of the molecule in an ionic way, you're going to end up with a basic solution. So, okay, NaOH, notice the OH is attached to the Na in an ionic fashion. Okay, same thing with lithium hydroxide. So these are both going to give you basic solutions. Okay, when we look at HClO3 and HBrO3, we know that the OHs that are present there are attached to the remainder of the molecule via covalent bonding, and subsequently these will give us acids in solution. Okay, so let's go ahead and discuss oxides in water. We've already looked at these before last semester. We basically talked about how covalent oxides and metal oxides behave in water individually. Okay, so covalent oxides, we know that they behave as acids in solution. Okay, and we've seen these examples before here. We have our SO3 interacting with H2O to produce H2SO4. Okay, and these all produce acidic solutions. Okay, when we deal with metal oxides, when we place them in water, we end up with our basic solutions. Okay, and so we know that whenever we place these types of substances in water, okay, that we're going to end up with either an acidic or basic solution. So obviously being able to identify covalent oxides and ionic oxides are going to be important for you guys to be able to make these types of assessments. Okay, so let's go ahead and move on. Okay, so let's look at another acid-base model. Today we're going to be looking, or in this section of the lecture, we're going to be looking at Lewis acids and bases. Okay, so the Lewis acid has its own definition. Okay, it's very specific in the fact that a Lewis acid is going to be the electron pair acceptor. Okay, so notice we're no longer talking about H plus in terms of identifying our acid. In the case of a Lewis acid, you have the ability to accept electron pairs if you are an acid. Okay, so basically that means that it's going to have, either an empty orbital or something of that sort to allow it to accept electrons from the Lewis base. So Lewis bases, in the other side of this is that a Lewis base is the electron pair donor. Okay, so we're going to go ahead and look at some examples of Lewis acids and bases. Okay, so if we go ahead and look here at boron trifluoride, okay, which is going to be a Lewis acid, okay, and ammonia, which is NH3, which is a Lewis base. Okay, what do we have here? We have basically this empty p orbital that's on this boron atom. Okay, and obviously we have a pair of electrons, a pair of lone pairs, or a lone pair set on this nitrogen. Okay, and we've just discussed that acids accept electrons in the Lewis base or Lewis acid base definition. Okay, and bases give electrons in the definition. So in this case, what's going to happen is the electrons in the Lewis base are going to be given or shared with the Lewis acid. Okay, so electrons are shared, and we form this kind of dative bond right here. Okay, so Lewis acid base definition, okay, acids are going to accept electrons, okay, and bases are going to give electrons. So obviously we're not talking about H+, we're not dealing with the hydronium ion at this point, we're just talking about electron transfers. So the nice thing about this definition is it opens up the Lewis acid base definitions and allows us to see why we have some pH changes with certain types of compounds. Even if they don't have, a hydrogen that can be ionized and produce H+ in solution. Okay, so basically other Lewis acid base reactions that we can look at here. Okay, notice we have aluminum +3. Okay, it's going to be able to accept electrons from the H2O molecules. Okay, it's going to form this nice structure here with the 6 hydrogens all bonded to that aluminum +3 ion. Okay, SO3, okay, and H2O. In that situation, you have a Lewis acid here and a Lewis base. Okay, and they basically transfer electrons to the SO3, and you subsequently end up with your product. Okay, so nickel 2 plus ammonia, right? You're going to have your Ni+2 floating around in solution. So this is going to be your Lewis acid. Okay, and you're going to have NH3 with its nice set of lone pairs. It's going to be your Lewis base. Okay, and we're going to have that transfer, and you're going to subsequently form a nice complex similar to what we have up here, which is going to be as follows. Okay, so let's go ahead and let's review a few miscellaneous facts that you may or may not be familiar with, but you should be familiar with by obviously test time. Okay, so we've talked about the acid ionization constant, and we've talked about pKa being an easier number to deal with than Ka, because it gives us a number that's a little more understandable. It's not some crazy long decimal or super small number with exponents. Okay, and basically we calculate pKa by taking the negative log of Ka. So pKa and Ka are inversely related with respect to the strength of your acid. Okay, so if you have a very large Ka, that means that you ionize a lot of your H+ in solution, so you have a strong acid. Okay, but when we take the negative log, obviously that changes our value, okay, and subsequently gives us an inverse relationship. So the smaller your pKa, the stronger your acid. Okay, and that's different than obviously your Ka. The larger its value, the stronger the acid. Okay, and the reverse is true. The larger your pKa, the weaker your acid, or the smaller your Ka, the weaker your acid. So make sure that you guys are comfortable with this concept, so that you're not saying, hey, I have this really big pKa, it must be a strong acid. Don't make that mistake. Okay, so this has been an assumption from the jump, but acids and bases, we know that they react with each other to form, a salt and water. Okay, when we are dealing with the reaction of a strong acid and a strong base, the salts that are produced basically do not affect the acidity or basicity of your solution, right? Na and Cl minus, Na plus and Cl minus would be an example of the salt produced when hydrochloric acid and sodium hydroxide react. So basically you end up with a neutral solution because, as we know, conjugate bases and things like that, and conjugate acids that are produced from strong sources are going to not affect your pH because they don't want to go back this other direction. Okay, so metals are going to react with acids to produce a salt and hydrogen gas. We've seen this on our single replacement reactions. This is actually one of the major examples that we use regularly. Okay, so if you take magnesium metal, react it with HCl, that's going to give you magnesium chloride, which is your salt. Okay, and of course your hydrogen gas, which would bubble up. Okay, when you deal with bases, bases do not react with metals. Okay, so you're not going to get that etching or things that you would expect, or hydrogen production, or any type of reaction that you would expect to get with acids. So metals and acid, going to produce a gas and a salt. Bases and acid, nothing. Okay, when you put a metal oxide with a strong acid, you're going to end up with a neutralization process. Okay, as we said, when we put metal oxides into solution, we know that we produce bases. Okay, and like calcium hydroxide and things of that sort. So basically, if putting this into water will give me a base, reacting it with an acid is obviously going to give me this neutralization process. Okay, obviously the reverse process there, if I take a metal oxide and put it in with a base, okay, there's no neutralization that can occur because we have two bases present in solution. Okay, so the volcano experiment that many of us probably did when we were little kids, or at least looked at, you took your vinegar and you took your baking soda, you put them together, and you subsequently got this nice bubbly volcano. Basically, what that is being caused by is the reaction of your carbonates with your acids in the acetic acid, and that process basically is going to produce a salt, carbon dioxide, and water. Okay, so if you react a carbonate or bicarbonate with an acid, you're going to end up with this neutralization process. So bases in this situation, if I take a base and I put it in the presence of a carbonate or a bicarbonate, that's going to give me no reaction.